Hello everyone. In this video we are going to start with the new unit, that is electromagnetic induction and alternating current. Now this electromagnetic induction and alternating current, according to NCERT, it has been divided into two chapters. Like first of all we will discuss the electromagnetic induction, the whole new topics we will be discussing, and then we will go for the alternating current. So the first topic that we are going to discuss in electromagnetic induction is magnetic flux. This is a very important topic. If you are not clear with this, then the other topics which are related to this won't be ever clear to you. So be sure that you are clear. Any doubts after the video, you can post me the doubts also. So here we are going to discuss magnetic flux. It is the first portion or the first topic of electromagnetic induction that we have just now started. So here, when we will consider magnetic flux, to explain the concept of magnetic flux, let me remind you that you have also studied electric flux. It is a kind of analogous situation in which in electric flux we have discussed it as the measure of the electric lines of force which passes perpendicularly through a surface. Now same is the magnetic flux also. It is that physical quantity which gives the measure of the magnetic lines of force which passes perpendicularly through a surface. That is, let me consider a surface here. Let me draw a surface. Let this be the surface, and a small portion of the surface also we are considering here. Okay, so let the total surface area can be represented as S also, A also, depends what you think. The small area, let it be given by ds. Now let's say the magnetic field lines are also shown here. These are the magnetic field lines which I am drawing here. Okay. So these shows a magnetic field, let it be given by B. B is the magnetic field here. Now we know the concept of area vector. The area vector is always perpendicular to the area. Now suppose we consider the small area ds. So the area vector will be perpendicular to ds. Let it be given by area vector ds here, which makes an angle of theta with the magnetic field. This angle is theta. Now if we want to find the flux linked with the small area ds, we are talking about magnetic flux. This flux linked with the area ds. Now this flux linked, the component of magnetic field along the direction of perpendicular to the area, that is along the area vector, will be given by b cos theta. So the magnetic flux, if it is given by d phi, will be written as the component of magnetic field along the area vector, which is b cos theta into ds, or we can write d phi as b ds cos theta, or in terms of dot product, d phi can be written as b dot ds. So you can see here the small flux which is linked with the small area ds will be given by b dot ds. It is the dot product of magnetic field and the area vector ds. Now if you want to find the flux linked with the whole surface, so for the whole surface, if it is given by phi, so we can write it as integration of b dot ds. That is the integration of the magnetic field. We are taking the dot product over the whole surface. So if we take the integration and take it over the whole surface, so flux can also be written as b dot the whole area if it is S, so we can write it in this form also. So I hope this is very clear to you. Now you need to understand a very important concept here. The value of magnetic field, magnetic flux, which we are getting as Bs cos theta for the whole area. Now this value of flux doesn't give the number of lines of force which are perpendicular to the surface, but it gives the measure of the numbers which are perpendicular to the surface. That means this value of magnetic flux is actually proportional to the number of magnetic lines of force which passes perpendicularly through the surface, right? So if this is the case, that these represent the magnetic lines of force which passes perpendicularly to the surface, through the surface, then the flux linked with the surface is given by this formula, which is Bs cos theta. So I hope this is very clear to you. Now you need to understand one more thing here. When we are discussing the magnetic flux, now the SI unit of magnetic flux is Weber. SI unit of magnetic flux is Weber. In short, it is WB. So we can write 1 Weber, 1 Weber WB is equal to, magnetic field can be considered as 1 Tesla into area is, magnitude wise it is 1 meter square. So 1 Weber can be written as 1 Tesla meter square. That is, we can define 1 Weber. Okay, 1 Weber may be defined as the magnetic flux linked through a surface which has an area of 1 meter square and through which a magnetic field of 1 Tesla is passing perpendicularly through its surface. I hope this is clear to you. 1 Weber may be defined as the magnetic flux linked with the surface of 1 meter square area such that a magnetic field of 1 Tesla is passing perpendicularly through the surface. Okay, so Weber is the SI unit of magnetic flux. Now if Weber is the SI unit of magnetic flux, then we should know the Cgs unit also. So let me rub this up first. The Cgs unit, we are going to calculate the Cgs unit. So let us see how it has to be calculated. Now you should first know what is the Cgs unit. The Cgs unit of magnetic flux is Maxwell. Cgs unit of magnetic flux is Maxwell. And Maxwell is represented as mx. So obviously 1 Maxwell will be equal to 1 Gauss centimeter square. Instead of Tesla meter square, which was for Weber, 1 Weber is equal to 1 Tesla meter square. So 1 Maxwell will be equal to 1 Gauss centimeter square. And there is a relation between Weber and Maxwell. We can easily find the relation. 1 Weber is written as 1 Tesla into 1 meter square, magnitude wise. We are not taking the dot product, we are taking the magnitude only. We just want to calculate the relation between Weber and Maxwell. Now Maxwell is represented as Gauss centimeter square. So 1 Tesla is equal to 10 raised to the power 4 Gauss, and 1 meter is 10 raised to the power 2 centimeter, but we have a square here. So we take the square, so it is 10 raised to the power 4 Gauss into 10 raised to the power 4 centimeter square. So it is 10 raised to the power 8 Gauss centimeter square, and Gauss centimeter square is Maxwell. So 10 raised to the power 8 Maxwell. So what we can write here, 1 Weber is equal to 10 raised to the power 8 Maxwell. This is the relation between the SI and the Cgs unit. So I hope this is very clear to you. Okay, now we can also find the dimensional formula of the magnetic flux. Okay, so let us see how we can find the dimensional formula. Let me rub off some part here. Let us calculate the dimensional formula here. So to calculate the dimensional formula, to write it in the form of M, L and T's. So let us see how it can be done. So we have the value of flux. We are just taking the magnitude. It is Bs. I am not taking the dot product. Only just I am writing the values of magnetic field and area, because we have to multiply this to get the dimensions of. So the dimensions of B. Now we can use a formula for force which has a B term, like force on a charged particle moving in a magnetic field. F is equal to Q V B cos sin theta, Q V B cross B. So Q V cross B, we have the formula Q V B sin theta we can write. So the value of B can be written as, sin theta don't have any dimension, so we can write F is equal to Q V B. So B can be written as F by QV. And the area vector here, it is area, so we can write it as S only. Now let us put the dimensions here. For force, we know it is MLT minus 2. For charge, which is I into T, current into time. Current ke liye we can write A, T is T here. Then for velocity, it is length by time, meter per second. Length by time is LT minus 1. And the area is meter square, so it is length square. So now we have, for flux phi, we can write here M. Then the value of L cancels out here. But this L square is there, so it is ML square. Then for T, you can see this T and T minus 1 cancels out, so we are left out with T minus 2 and A minus 1. So I hope this is very clear to all of you. Okay, so we have a relation here for the magnetic flux, which is ML square T minus 2 A minus 1. Now the dimensions of magnetic flux is also very clear to you, I suppose. So we have just now seen that how the magnetic flux can be defined. Okay, one more thing quickly let me discuss here. Suppose a surface is there, okay, and this is the direction of magnetic field, applied magnetic field. Now the area vector here for this base, it is in this direction, but for this here, area vector is always outward to the body. So here this is the area vector, and here suppose we write it with the symbol S here. So area vector is in this direction, and here area vector is in the opposite direction. So the flux linked with this surface, which I am showing here, will be positive, because B and S have the same direction. Angle between them is 0. B dot D will be B dot S will be BS cos 0, which is positive value. But here the magnetic field is in this direction and area vector is in the opposite direction. So B dot S will be BS cos 180, which is minus 1. So here the flux linked will be negative, and here the flux linked will be positive. So we can have positive and negative flux linked also. So you need to understand the concept and the direction between the magnetic field and the area. So I hope this is very clear to you. Any doubt, you can post me the doubts. Thank you.